All right, so let's have a look at our first example here. So in the first example, it's the easiest one, right? We're just looking for the number of moles. We're not going to have to manipulate the mole equation. We're solving for n, okay? So in this one here, it says how many moles, so n is our question mark, okay, of calcium carbonate, right? So we got to calculate big M, the molar mass here. So we got calcium, which is 40.08, okay, plus how many carbons? 1, okay, and 3 oxygens. Okay, so we got, whoop, works better when it's on, 40.08 plus 12.01 plus 48, which is 16 times 3. Okay, so 100.09 grams per mole. Okay, so we've got big M. They also tell us in the question that the mass, or little m, is 125 grams. So clearly I have a little bit more than 1 mole here. Okay, everybody follow me there? Okay, so I'm looking for the number of moles now, so n equals little m over big M, and like we said, we don't have to manipulate here because we're solving for the number of moles. We just have to plug in. 125 grams was our mass, 100.09 was our molar mass. Okay, so we'll take our 125 and divide it by our answer. Okay, so we get 1.25 moles. Okay, questions on that one? All right, so that's a 3-mark question. You get 1 for your molar mass and givens, okay, 1 for your mathematical operations, and 1 for the answer. All right, our second example, I'll walk all the way through it here. Okay, so what's the mass of 2.7 moles of lithium phosphide? Okay, so we got another ionic compound there. So 2.7 moles is N. Okay, they're asking us to calculate the mass, so that's our unknown. And because they told us what stuff we're dealing with, we can calculate the molar mass. So we're dealing with lithium phosphide. So lithium is 6.94, and there are 3 of them. And then we got phosphorus, which is 30.97, right? And there's only 1 of that. Okay, so we'll have our 6.94 times 3 plus 30.97, giving us a molar mass of 51.79 grams per mole. Okay, so I've got N and I've got big M. I'm looking for little m. So the formula sets up like this. Okay, I need to move big M over to the other side. So I'm dividing by it right now. So to move it, I do the opposite. What I do to one side, I do to the other. And now I have my new formula solving for M. Okay, so M is going to equal 51.79, big M, our molar mass, multiplied by the number of moles, N, which was 2.7. All right, so we got 139.83 grams. Okay, so that would be a 4-mark question. 1 mark for your givens, 1 mark for your manipulation of the formula, 1 mark for plugging in the numbers, and 1 mark for your final answer. Questions on number 2? Okay, how many people are done or stuck on 3? Okay, let's have a look at number 3, and then we'll see about number 4 here. Okay, so on number 3, they're asking us now for the number of molecules. Okay, so this has an extra step in it involving Avogadro's number. We're going to use the mole equation, and then we're going to use Avogadro's number with whatever we calculate there. Okay, so overall, we're looking for the number of molecules. That's our question mark. Okay, they tell us the material. It's iron 3 oxide. Okay, so we got Fe2O3. Okay, so that's going to be 55.85 times 2 plus 16 times 3. Bless you. Okay, 55.85 times 2 plus 48. Okay, 16 times 3. So 159.7 grams per mole. Okay, and they also tell me the mass, 230 grams. All right, so looking at this right now, I can calculate N. I can get the number of moles. Agreed? That's not the final thing I'm supposed to find, but it'll help me get there. Okay, because right now I have the other two parts of the mole equation. So N equals little m over big M. Okay, the mass, little m, was 230 grams. Okay, divided by the molar mass, which was 159.7 grams per mole. Okay, so 230 divided by 159.7. All right, so I have 1.44 moles. All right, now, what does Avogadro's number tell me again? What does it mean? It's the number of, yeah, or particles, let's say, so we can be kind of more accurate. The number of particles of any material that are in 1 mole, okay? That is the importance of Avogadro's number, and that is the thing we have to understand about Avogadro's number. Otherwise, it becomes difficult to figure out what to do with it. Okay, so it is the number of particles in 1 mole. I know how many moles I have, 1.44. And now I can use Avogadro's number with that to figure out the number of molecules. Okay, so the number of molecules in 1 mole is this. And I have this many moles. What do I need to do with those two numbers? Multiply them, right. That will give me the number of molecules. Okay, so remembering, when we want to enter Avogadro's number, we have to enclose it in brackets, 6.02, and then hit your exponent button, whatever it happens to be on your calculator. Okay, 23 end bracket. All right, so we're looking at 8.67 times 10 to the 23 molecules. Okay, whenever you use Avogadro's number, you're only going to do one of two things with it. You're either going to multiply by it or you're going to divide by it, and nothing else. Okay, it's never going to be part of the mole equation. Okay, so never substitute it into there. Okay, it's always going to be a separate step with that. Now the marks for that one, again, this is a 4-mark question. 1 for the givens. Okay, 1 for calculating the number of moles. Okay, 1 for doing this operation, and 1 for the final answer. Question, Nick. As long as you didn't put in an extra 10, yeah. Okay, just be cautious doing it that way. Like I say, I tell people to do it that way because people mess up more often doing it the other way. Okay. All right, everybody follow there. Okay, how many people have done question 4? Okay, let's just go over number 4 for the sake of going over it right now. Okay. Okay, so in question number 4, they give me now the number of molecules. Okay, so I'm given the number of molecules, but I'm being asked to find the mass. So mass is our question mark here. Okay, I have the number of molecules. Now, in the last question, I just used Avogadro's number multiplied by the number of moles to get the number of molecules. What do you suppose I need to do with this one? Yeah, I already have the number of molecules, so now I want to divide by Avogadro's number, because what will that give me? The number of moles, right? Okay, so number of molecules is 5.42 times 10 to the 21, so a lot less than a mole. Okay. The other thing we know is we can calculate big M because we are dealing with nickel 2 nitrates. Okay, so molar mass of nickel is 58.69. Okay, and there's only 1 nickel here. How many nitrogens are there? 2. How many oxygens? 6. All right, so 58, let's clear everything here. 58.69 plus 28.02, that's 14.01 times 2, okay, plus 16 times 6. All right, so 182.71 grams per mole. All right, so if I'm going to calculate M, I need big M and I need N. So I've got to use the number of molecules and Avogadro's number to get N. Okay, so N will be 5.42 times 10 to the 21, the number of molecules I have, divided by the number of molecules in a mole. So I'm just going to put the units on here so you see what we're doing. Okay, molecules, and then 6.02 times 10 to the 23. And really what this is saying is molecules per what? Per mole. All right, what's going to cancel here? All right, now I'm going to be left with moles. Okay, I don't know if that helps you. Sometimes unit analysis helps people see what they're doing. Okay, all right, so now we got to look at what are we going to get for a number here. So we've got in brackets 5.42 E21, okay, divided by Avogadro's number. All right, so we're looking at 0.009 moles. So like I said, a lot less than a mole. No. Usually what we do in science is we keep all our decimals till the very end and then round. Okay? Yeah, round your final answer, not your intermediate answers. Okay, is generally what we do, especially when we get to like grade 11 chemistry and physics and stuff when you work with significant digits. Okay. All right, so 0.009, okay, is our number of moles. Now that I have N, I can calculate M. All right, so now I'm going to go back to the mole equation. Little m over big M. Solving for little m means multiplying both sides by big M. Okay, so little m will equal 0.009, the number of moles, okay, times our molar mass, which was 182.71. Okay, and like I said, we want to keep all of our decimals kind of till the end, right? Which is why I try and do it in a certain order so that I can just go answer, right? And then I keep them all that way. Okay, times my 182.71. All right, so I got 1.64 grams. Not very much. Okay, so that's the 5-mark type of problem. Okay, 1 mark for the givens, 1 mark for calculating the number of moles, 1 mark for the manipulation of the mole equation, 1 mark for plugging in the numbers, 1 mark for the final answer. Okay, remember, there's only 4 ways. These are them. This is exactly like the 4 I went over yesterday. These ones I got from the unit exam 2 years ago. Okay, so I'm showing you exactly the kind of thing I'm going to ask next week. Okay, you guys have a pretty good idea here of the level of difficulty you're going to see. It's not going to be any different than this. Okay, so looking at number 6, there's essentially kind of 2 ways to go about this, but what it's asking really is, do you understand the difference between a molecule of oxygen gas and an atom of oxygen? Okay, this question is asking how many oxygen atoms are in 64 grams of molecular oxygen gas. Okay, so what I need to do is set this up like a regular mole equation and figure out how many molecules of oxygen are in 64 grams. Okay, that's how I want to start it. So we have 64 grams as our mass. Okay, I can calculate N because I know that I have 64 grams, and I know that the molar mass of oxygen gas is how much? 32, because it has 2 oxygens in it. Okay, so 32 grams per mole. So when I do this, I find out that I have exactly 2.0 moles of oxygen gas. Everybody all right with that? Okay. So now that I have the number of moles, I can take that and multiply by Avogadro's number to get the number of molecules of oxygen. Everybody okay with that? Okay, but remember, this will give me the number of oxygen molecules, not the number of oxygen atoms, okay? Because I used the molar mass of oxygen gas. Okay? So if I take that, I go multiply by Avogadro's number, so essentially I'm just going 2 times 6.02 times 10 to the 23. Okay, so basically I'm just doubling it, so it's going to be So 2 times 6.02 E23. Right, whoop, what did I do wrong? No, L, that's not what I want. 2 times, there we go, 23. All right, so I get this. I get 1.204 times 10 to the 24. That's how many molecules of oxygen gas I have. How many atoms in each molecule? 2. So what do I do with that number again? Multiply by 2. Okay, so that's one way to do it. Now I've got the right answer, 2.408 times 10 to the 24 atoms of oxygen. Okay, the other way to do this would be, instead of using the molar mass of oxygen gas, I could use the molar mass of an oxygen atom. In which case, this number is not going to be 2, it's going to be 4. So now I'm going to have 4.0 moles. So now I go back over here, and I go 4, I keep the n there, I go 4 times Avogadro's number, and I get straight to this number. Either way will work. Okay? The question is mostly just asking whether you understand the difference between a molecule of oxygen and an atom of oxygen. That's really all it's asking. Okay? Okay, any of these other ones giving us trouble? We need to go over. Okay, there's a little bit of a trick down in number, which one was it now? Number 11 here. Okay, I know a few people have looked at this one, and because it was in exponent in scientific notation, they were using Avogadro's number with it. But remember, this is in grams, so it's just a mass. Okay, it's little m. It's not a number of molecules or anything. All right, keep her going then, guys.